Hi guys, this video is an introduction to partial fraction decomposition. I'm going to call it PFD occasionally. It's going to allow us to antidifferentiate rational functions. It's really an algebraic method. It's basically going to allow us to take a rational function, which is a polynomial divided by a polynomial, and write it as a sum of what are called partial fractions. And before we get into how to write this polynomial over a polynomial as a sum of partial fractions, I'd like to go over some guidelines. I've written down a lot of them before I created the video. Toward the end, I'm going to start writing as we go. But here are your guidelines. When you see a rational function, you've got the antiderivative of this over this, you always want to try your basic antidifferentiation rules first. If you just had a constant over x squared plus a constant squared, that would be an arctan, so your basic rules would work. Or if you just had a linear polynomial in the denominator, maybe you could do a u sub. But you should try the basic rules first, and if basic rules fail, try u sub. If you are doing u sub with a rational function like this, u is usually your denominator. So you'll take the derivative of the denominator and see if a constant times that derivative is up here. If it is, you can do the u sub. If not, then you want to try partial fraction decomposition. So always ask yourself if basic rules work first, then do u sub, then do PFD. Now, if the degree of the numerator is greater than or equal to the degree of the denominator, the first thing you want to do is long division. Like, here's an example where I would do long division first. If you don't remember, the degree of a polynomial is the highest power of x in that polynomial. So this is a degree 3 polynomial, and this is a degree 2 polynomial. So the degree of the numerator is greater than this one. So if the degree of this is greater than the degree of that, we're going to do long division first. After you do long division, you're going to have your polynomial divided by your divisor equals some quotient. It's going to be a different polynomial, plus your remainder over your divisor. That was your original denominator. Whenever you do the division algorithm, you're going to end up with this polynomial. That is something that you can antidifferentiate using basic rules. The remainder over the divisor is going to be a good candidate for PFD. The degree of the remainder is always less than the degree of the denominator or the divisor. Just according to the division algorithm, we know we're at the remainder. We know to stop when the degree of the remainder is less than this. So you're going to take this, you're going to rewrite it like this, and then you're going to antidifferentiate this polynomial, and you're going to use PFD for that one. So if the degree of the numerator is greater than or equal to the degree of the denominator, do this first. If not, if the degree of the numerator is less than the degree of the denominator, you want to use PFD. And the first thing we do in order to state the form of the partial fraction decomposition for a particular rational function is we factor the denominator as much as possible. And that means we're going to factor it into linear factors. They're going to look like a line, like y equals mx plus b, factors that look like that, plus irreducible quadratic factors. And these are quadratic expressions that cannot be factored in the real number system. That means if you were to look for the roots of this quadratic polynomial, you wouldn't find any, not in the reals. The parabola that you would draw, it never crosses the x-axis. And that's because the discriminant, this b squared minus 4ac, is going to be negative. If b squared minus 4ac is negative and you are solving this set equal to 0 and you're solving for x, then you're going to get complex answers. Like you might get plus or minus 4i or 2 plus or minus 7i. You might get something like that. That tells you that this cannot be factored further. And in algebra class we called it prime. In this class we call it an irreducible quadratic factor. So here's just a couple of reminders. It's probably been a while since you factored anything. Well, not too long. I mean, I guess you did some factoring in Calc 1. But this is a difference of squares. If I've got a squared minus b squared, it factors to a plus b times a minus b. So keep that in mind. Comes up surprisingly often. Textbook authors like that. This factors to x minus 1 times x minus 1, which is x minus 1 squared. Something like this. Notice you've got an x to the fourth and an x cubed and an x squared. You always want to factor out that greatest common factor first, and these all have an x squared in common. So we factor out the x squared. I ask myself x squared times what gives me x to the fourth. X squared works. I say x squared times what will give me negative 6x cubed. X squared times a negative 6x will work, and x squared times 8 gives me 8x squared. And then I leave this alone. I'm just going to bring it with me because it's still there. If I want to keep everything equal, it still has to be there. But I'm going to focus on this. I'm just going to factor that part. And that factors to x minus 4 times x minus 2. Now this is a sum of squares. A squared plus b squared is prime. And prime is another way of saying it's an irreducible quadratic. This is actually the form of most of our irreducible quadratics in this class. It's going to be your variable squared, x squared or u squared or something like that, plus a constant. If you see that, then you know it's an irreducible quadratic. Now this one is x to the fourth plus 25x squared plus 144. This actually looks a lot like this. So I'm going to look for two numbers that multiply to give me 144 that add to 25. And instead of factoring this with an x plus a constant times x plus a constant, since that's an x to the fourth and that's an x squared, I'm going to use an x squared here and an x squared here. And you might say, how do I know I can do that? Well, you don't know it's always going to work. You don't never know for sure that a polynomial is factorable. But if I see an x squared term and an x to the fourth term, I'm thinking this way. I'm thinking this is a possibility at least. I need two numbers that multiply to give me 144 that add to 25. It turns out that plus 9 and plus 16 work. 9 plus 16 is 25, and 9 times 16, it's 3 times 3 times 4 times 4. It's going to give me 12 times 12, 144. So this is a product of two irreducible quadratics. So remember that you can do that. If you have something like this, it can factor this way. And then at this point, after I've factored it, I would look at each factor separately and see that is an irreducible quadratic and that is an irreducible quadratic because I've got a sum of two squares for both of them. Now, if that was an x squared minus 9, which could just as easily have come up with something that looks like this, I would have to factor that further. But since it's a sum of squares and a sum of squares, there's nothing left to do. Now this is an irreducible quadratic, but it's not obvious. You might say, oh, I need two numbers that multiply to give me 5 that add to 4. Well, you're not going to find any. One way that I can tell that this is an irreducible quadratic is I can write this as a sum of squares like this, just by completing the square. So I'm going to complete the square and show you that this is a perfect square plus a constant. So remember how we did this when we were completing the square in section 8.1. We identify b, take half of that, and then square it. 2 squared is 4. So we add 4 to complete the square and then subtract 4 to compensate for that. So this is giving me a perfect square that's x plus 2 squared, and 5 minus 4 is 1. That's u squared plus 1 squared. So that's an irreducible quadratic, that's prime. You could also identify a, b, and c. A is the coefficient of x. B is the coefficient, or x squared, excuse me. B is the coefficient of x, and c is the constant term. Notice that b squared minus 4ac, that's 4 squared minus 4 times 1 times 5, 16 minus 20. Notice that that's a negative number. So if I were to solve this, set this equal to 0 and solve for x, I'm going to get some complex numbers in my answer. I'm going to have this negative under the radical when I use the quadratic formula, which means that this has complex roots, and if it has complex roots, that means when it factors, it has complex factors. So that's another way to tell that it's an irreducible quadratic. You can either complete the square and see that you've got u squared plus a constant. If it's minus a constant, it might be factorable. But if it's plus a constant, it's prime. But most of the time in our class, whenever you see an irreducible quadratic, it's going to look like this. Okay, so that was our little factoring review. I did not practice factoring trinomials, but you should look that up if you need to. So again, with PFD, if the degree of the numerator is less than the degree of the denominator, you don't have to do the long division, and you want to factor the denominator as much as possible. Now, once it's factored, it might look something like this. Maybe you've got 2x minus 1 over x plus 5 cubed times x squared plus 1. Now, I probably wouldn't have you factor that because that's a 5th degree polynomial once it's all multiplied out. But you're going to have linear factors, like that's an x plus 5 is a linear factor. It's repeated 3 times. And you're going to have irreducible quadratic factors. That's my irreducible quadratic x squared plus 1. It's not repeated at all. Actually, for the sake of our example, let's make it repeated twice. And let's add another factor that's not repeated. Let's do 2x plus 3. Okay, so you're going to have a polynomial over a polynomial, a rational function that looks like this. And you're going to have some linear factors that aren't repeated. You're going to have linear factors that are repeated. You're going to have irreducible quadratic factors that may or may not be repeated. The question is, what does the partial fraction decomposition look like? Well, it turns out if this linear factor raised to the n is a factor of your denominator, then for each power of that linear factor, you're going to see a term in your partial fraction decomposition. I'll have a constant over my linear factor plus a constant over my linear factor squared plus a constant over that linear factor cubed. And I keep going until I get to that power, whatever that power is. And it's the power in the decomposition over here. It's the highest power of the factor when you write it down. Since there are n of these, I'm going to have a n over mx plus b to the n. So I'll have n terms. So this x plus 5 cubed, I would get a constant over x plus 5 plus a constant over x plus 5 squared plus a constant over x plus 5 cubed. And then I would stop just for that part. That's what this tells me. Now, any linear factor behaves this way. That's just a linear factor by itself, so I'm going to get a constant over that linear factor as part of my decomposition. So that's how we handle the linear factors. Now, if an irreducible quadratic, ax squared plus bx plus c, is a factor, and we're assuming it's an irreducible, so b squared minus 4ac is negative, then this is what you're going to see in the partial fraction decomposition. Every irreducible quadratic gets a linear expression in the numerator. So this is degree 1, and in the numerator we get something that's degree 0. We just get constants. This is degree 2, in the numerator we're going to get something that's degree 1. It's 1 degree less. So I'm going to see ax plus b over that, plus cx plus d over that squared, and so on until I get to ax squared plus bx plus c raised to the n, whatever that power is. So if that was squared, I'll have 2 terms. If there's just one of those, I'll have 1. If that's cubed, I'll have 3 of them. If that was raised to the 5th, I'd have 5 terms. And this guy over here, I'm not really sure what it would be. I'm just going to write a star x plus b star, little stars just to denote that they're different numbers. but I've got a number times x plus a number over here, and I get that for every single term, or excuse me, every single part in the partial fraction decomposition. So over here in our example, I had, excuse me, I had a linear factor cubed, so I have that constant over the factor plus the constant over the factor squared plus a constant over the factor cubed. I have a linear factor to the first, so I get a constant over that factor. And then this is an irreducible quadratic squared. So I'm going to have a constant times x plus a constant over my irreducible quadratic plus a constant times x plus a constant over my irreducible quadratic squared. And this is equal to that up there. All right, for some choice of A, B, C, D, E, F, G, and H. Now there's no way I'm going to assign a problem for you where you have to find A, B, C, D, E, F, G, and H. But I want you to be comfortable writing down the partial fraction decomposition for different expressions. So let's do a few more examples of that. Got some examples around here somewhere. All right, so let's just practice writing the form of the partial fraction decomposition. So let's say you've got 5x plus 3 over this. Well, that's easy. I've got two linear factors, neither one of them are repeated. So I'm going to get a constant over my first linear factor plus a constant over my second linear factor. And what about this? Now in this case, the denominator is not factored yet. There are two possibilities. Either it factors, and I can do the same thing that I did up here, or I complete the square, and using a little bit of algebraic manipulation, it might be an arctan or a u sub or something like that. But if it factors, I want to factor it, so I'm going to try to factor it. Leave the numerator alone. The numerator does not come into play here at all unless it cancels with something in the denominator. Okay, so I'm looking at this. I need two numbers that multiply to give me negative 28 that add to negative 3. Well, if the product is negative, that means I need a negative and a positive. So what I'm really looking for is two numbers that multiply to give me 28 that have a difference of 3. 4 and 7 will work, won't they? Because they have a difference of 3, and 4 times 7 is 28. Which one has to be negative so that the sum is negative 3? I guess it's the 7. Negative 7 plus 4 is negative 3, and negative 7 times 4 is negative 28. So I'm going to have a negative 7 and a plus 4. All right, so I've got two linear factors. Neither one is repeated. So I have a constant over the first factor plus a constant over the second one. For some choice of A and B, and I'm going to find them. I'm going to teach you how to find them in the other videos. This is equal to this. And A and B are just constants. They're never functions of x. So I have a constant over this plus a constant over this is equal to this. And this I can antidifferentiate. If that's a constant, that's just a u sub, and it's going to become a logarithm after I antidifferentiate. And that's another u sub logarithm. And that's a u sub logarithm, and that's a u sub logarithm. So all of these are going to work just fine. Okay, so let's do another example. Okay, I've got degree 2 up here, degree 3 down here, so it's a good candidate for partial fractions. I need to factor my denominator as much as possible. Now a lot of students look at this and they freeze. They say, oh, it's only binomial. Like, what am I supposed to do? Is it really factor? It does really factor. You have to factor out the greatest common factor first. So I look at the 5 and the 2. They don't have anything in common, so I'm not factoring out a constant. But then I look at the x cubed and the x to the 4th. Well, that's x times x times x, and that's x times x times x times x. They both have 3 x's in them, so I can factor that out. Leave the numerator alone, unless it factors. Don't be distracted by it. All right, I've factored out an x cubed. I ask myself, x cubed times what gives me 5x cubed? And that's a 5. And then I ask myself, x cubed times what gives me negative 2x to the 4th? I need a negative 2. And I had 3 x's. I need one more to get an x to the 4th. So we're there. All right. So I've got 1, 2, 3 factors and a 4th factor. Now this x cubed, a lot of students say, wait a minute, Miss Townsend, that is a cubic factor. I thought you said everything would factor into linear factors and irreducible quadratic factors. You didn't tell me that there would be any cubic factors. Yes, you're right. That's not a cubic factor. We don't want to think of it as a cubic factor. Think of that as x minus 0 cubed. That's a linear factor repeated 3 times. That's y equals x repeated 3 times. That's how I want to think about it. So when I write down my decomposition, my factor is x, and I'm going to have 3 terms associated with that x because it's cubed. So we're going to have a constant over our linear factor plus the constant over that linear factor squared plus a constant over that linear factor cubed. And this is a linear factor. So we're going to have a constant over that factor. And that's a log when I antidifferentiate. That's a log after doing a u sub. That's an x to the negative 2 power rule, x to the negative 3 power rule. A, B, C, and D are constants that we're going to learn how to find in the other videos. Okay, last example. Okay, so I've got x to the 4th minus 16 in the denominator. That's good. That's a difference of squares. X to the 4th is x squared squared, right? Add the exponent, or excuse me, multiply the exponents. That's our rule. X to some power raised to some power is x to the product of the powers. So x squared squared is x to the 4th, and 16 is 4 squared, so I can add 4 and subtract 4. This is a squared minus b squared. A is x squared and b is 4. So you have a plus b times a minus b. A lot of students say, I've got 2 irreducible quadratics from here, but they're wrong. Do you see their mistake? This is an irreducible quadratic. That is a sum of 2 squares. So that I can write in my partial fraction decomposition this way. I have an irreducible quadratic, so I get a linear expression in the numerator and my irreducible quadratic down here. But be careful about this. That's also a difference of squares, so we can factor that further. So I've got a linear factor and a linear factor. So I'll have a constant over the first linear factor plus a constant over the second linear factor in my partial fraction decomposition. Okay guys, that's it for the basics about partial fractions. If you have linear factors, this is what the decomposition looks like. If you have linear repeated factors, if it's repeated 3 times, you get 3 terms, 1, 2, 3. All the way up, you have that mx plus b squared, mx plus b cubed. Whatever that power is, that's where you stop. That's how many terms you get in the decomposition. And if it's an irreducible quadratic, remember you get a constant times x plus a constant in the numerator. And even if it was repeated, you'd get a constant times x plus a constant over that factor squared or cubed, depending on what the original expression looked like. So that's it for that. Watch the other videos if you want to learn how to find A and B and A, B, C, and D, or A, B, C, and D. Quickly, we're going to use 2 methods to find A, B, and C. are the constants A, B, C, and D. When you have linear factors, you're going to choose x values to simplify a certain equation. When you have irreducible quadratic factors, you're going to set up and solve a system of equations. To find your constants. Okay, the other videos will show you how to do that. And that's it.